you have read the paper? Like one? There's like 40 pages in there.
I was reading for a class.
Oh, you've read it for a class?
I read the title.
Okay. For most of you, this is going to be a high-level talk. I'm not going to go deep into the proofs, mainly because the paper I posted is like 38 pages long. Some of the proofs have like a dozen lemmas, and the entire proofs cover like 10 pages each. So not going there. On the agenda today, I'm going to talk a little bit about the history of failure detectors in distributed systems. I'm going to talk about the failure detectors themselves. And finally, I'm going to very hand-wavy go over the part where you can use failure detectors to solve distributed consensus. That's a note. I'm not an expert in this. I'm probably going to be wrong for some things. If you want the major details, you should check out the paper. Hopefully I give you a good idea of what weakest failure detectors are about, but, so we'll start with the history. So part of the history starts with the original paper itself. Weakest failure detectors are solving consensus, and a companion paper, Unreliable Failure Detectors for Reliable Distributed Systems. It's 1995, 1996 there because I found multiple copies with different dates, but on ACM it's 1996 for both copies. So these were the seminal papers that described weakest failure detectors in distributed systems. The reason I'm talking about these papers and the reason I love these papers is because the second author of that first paper is Vassos. I can't pronounce his last name, but some of you who were in school with me, we were taught algorithms and data structures by this professor at U of T. So at some point I learned that he had received the Detector Prize, which is an award, an ACM award for excellent distributed systems papers. He and the other two authors of that paper there. So I tried to find out why these papers are such a big deal. Well, to find out why they're such a big deal, we're going to have to go back to the late 80s, before these papers existed. And the main paper I'm going to talk about in the 80s is impossibility of distributed consensus with one faulty process, or the FLP result, as it's more commonly known. FLP because the first letters of the three authors are named in order. So, yes.
Not algorithm by Nancy Lynch.
Yeah. Well, it's really hard not to find a paper by Nancy Lynch somewhere when you talk about distributed systems. So the FLP result basically says, in an asynchronous system, consensus cannot ever be reached if even one failure exists. When I say asynchronous, I mean a system that makes no timing assumptions. So you don't know how long message delay could be. It could be infinity. You don't know how far clocks in each process have drifted, and you don't know how long it will take a process to process a message. In terms of consensus, we mean the majority of processes agree on the same value. So if you have 3 nodes, at least 2 of them have the same value x. Why this asynchronous system is important is because there's also synchronous systems where you know the bounds of your message delay, of processing time, of clock drift. Synchronous systems are easy to think about, but hard to implement. Asynchronous systems with less restrictions are are somewhat easier to implement in a sense. If you've ever tried like dealing with time zones, you know that dealing with times is hard and sucks. You're better off never dealing with time. So people wanted to create distributed systems that would work under asynchronous systems, but the FLP results showed that consensus is impossible. And consensus can be mapped to different things like you can map consensus to having multiple databases agree on the same value, or having multiple load balancers agree that this one service is too overloaded, we should talk to the others. Lots of different problems are basically consensus if you boil it down, which is why this is important. But some other papers in the late 80s, which I've written down there, showed that.
David, just a quick question. So, a faulty process in this case is like a failed stop, or is that actually many issues?
A faulty process would be one that I'm going to get to that, but it's basically one that just stops replying to messages. Yeah. So these papers in the late 80s that I posted down there, they showed that in between synchronous systems and asynchronous systems, you can have partially synchronous systems. So systems where maybe you know you have an upper bound for message delay, but you don't know how long processing time takes, or some of the restrictions are lowered. So in these systems, you can solve consensus. So then, after these papers came out, the question became what's the least synchronicity needed to solve consensus? How much below asynchrony can you go where you can solve consensus? But with the failure detector papers, one thing they noted was that if you look at what the FLP result says, the major issue is that in an asynchronous system, you can't tell whether a process has failed, so just stop dead, or the process is super, super slow because message delay is unbounded and processing time is unbounded. So you could be waiting infinitely long for a reply. That doesn't mean the process has failed, you just don't know. So in that under those kind of conditions, you can't have consensus. So one of the things the authors of the failure detector papers noticed was that you can change this. You can change the problem of partial synchronization to failure detectors. So instead of thinking how much sync do you need, you could think about it in the sense like how much information does a failure detector have to give me in order to solve consensus? So a weak failure detector is one that just gives you little information. So it might give you the right answer or the wrong answer. This is why they won the Detector Prize, was because this opened up a new framework of thinking about consensus in an asynchronous environment.
Sorry.
Yes.
So the output of the failure detector is simply a predicate of is this node failed or not, yes or no, or which node is failed. What is the output of a failure detector?
I want to get to that, but in the papers, the output of a failure detector is it keeps a list of processes it suspects has failed.
Okay. And so when you say the weakest, if the output is fixed, it means it is like missing something, like.
It might be missing something. It might wrongly suspect a correct node, or it might not suspect a node that has failed. Which brings us to the part about failure detectors. Another note, in both papers, when they describe failure detectors, they describe them abstractly. They wanted to produce a new framework of thinking about distributed systems and asynchronous systems. They didn't give any implementation details. Later papers that came out after actually showed how you could create a weakest failure detector. So here's what I tried to describe a failure detector. So a failure detector D maintains a list S of processes P it suspects has failed. So failed means that the process has crashed, and when a process crashes, we assume it doesn't restart. We just don't let it restart. Or process is for some reason faulty, so it might be really slow, or the network in between it might have just collapsed and you never got the reply that it sent. So it keeps a list of nodes it thinks has failed, whether or not ignoring the network system. So in the diagram I made, if you have 3 processes, P1 to P3, each one has attached a failure detector, D1, and the failure detectors will pass each other who it suspects has failed, and they'll communicate that way. How the failure detectors actually work depends on the implementation, depends on the environment it's implemented in, which is why the paper authors never discussed that. Future papers do discuss that problem. But the important thing about failure detectors is that they have 2 abstract properties: completeness and accuracy. All failure detectors in these papers have these properties, and these 2 properties can be described as either strong or weak. So I'm going to start with completeness. So we're going to start with strong completeness. So strong completeness means that every faulty process is eventually permanently suspected by every non-faulty process. So if a node fails, all the other processes are still up. By being up and running, they are correct. Those processes will eventually suspect that node has failed, has crashed. It could be some amount, after some amount of time, in strong completeness, all the failure detectors will suspect that the failed process has failed. Do you all get that? Yeah? So with strong completeness, we can talk about weak completeness, which is some non-faulty process knows that a failed process has failed. Some, not all of them, just one or more. So in this case, in the diagram, you have one failed node. Eventually, after some point, one of your other processes knows that it failed. That's weak completeness. Now let's talk about accuracy. We have strong and weak accuracy. So strong accuracy is no process is suspected before it crashes, which just simply means that if you have a process, if it hasn't crashed, it will never be considered, it will never be suspected. Once it's crashed, it can be suspected by all the other processes. Weak accuracy just says that there exists at least one correct process that never gets suspected. One problem the paper authors found with accuracy is that guaranteeing these might be really, really hard. So they added 2 extra characteristics, which are eventual strong accuracy and eventual weak accuracy, which simply means you take the previous definitions and add that sentence. After some initial period of confusion, so when the nodes start up, it might be chaos, they have no idea what the heck is going on, but eventually they'll, whether it's strong or weak accuracy, they'll fulfill their own properties there, after some time. That's all the eventual means, after some time. So if you put this into Excel or something, you get a table of 8 different classes of failure detectors. By classes I mean all failure detectors that can solve consensus fit into one of these categories, so one of these classes. So depending on how you implement it, it might belong in one of these 8. So you got strong completeness, strong accuracy, which would be a perfect failure detector. You have strong completeness, and eventually weak accuracy, which would be an eventually strong failure detector. I didn't name these. These came from a textbook I found, which I linked describes a way of not having to think about 8 classes, but thinking about less. They found three properties, idea, characteristics that hold. Strong accuracy or weak accuracy, or their eventual equivalents. The strong version is always the strong version is a superset of the weak version. So anything a weak accuracy failure detector can do, the strong version can do it. That seems obvious. So the blue arrows there show that strong can do anything weak can. Yeah. The second characteristic is that any strongly accurate failure detector can do anything the eventually strong accurate failure detector can do. That seems obvious because if you just change that time of chaos to 0, it's that, basically. The last one is the one I'll go into detail about. It says that any strong complete or weak complete failure detector is equal to each other. Any eventually strong complete failure detector is equal to an eventually weak complete failure detector. So in this table, the columns there, those two failure detectors are equal. They're equal in the sense that there's an algorithm to take a weak version, a weakly strong version of the failure detector, and make it so that you can use it like it was a strongly correct failure detector. So that's a Q, by the way, a cursive Q. For those of you who don't know cursive, the weak completeness failure detector there can be turned into a perfect failure detector through the algorithm I will describe, which the textbook I use called the boosting. So you can boost the failure detector. So you're making the strong complete and the weak complete equal. And a high-level version of the algorithm is you have your failure detector. It's got a set S that you set the empty set. That set is the list of processes it suspects has failed. While it's running, you constantly broadcast S to all processes, to all, including yourself. If you ever receive a S prime from another process Q, you take the union of your S and the S prime, remove the Q from it. So what this allows is, so what that last line is doing basically is, in a weakly complete failure detector, you're gonna get. What if I show you? Was it weakly? No, it's about weak accuracy. Sorry. In a weak accuracy failure detector, some node is going to be suspected of failing, even though it hasn't. Some node is never suspected. Sorry, give me a second. I got lost myself. This is embarrassing.
This is for completeness.
Yes, it's for completeness. Oops.
Some node suspects another, it's going to be broadcasting the other one's receiving it.
Well, we are not assuming that there are any adversaries, right? So as long as
Yeah.
one detects and you have a mechanism of being able to share that knowledge, then you're good.
And the key is the one that's detected it permanently knows that it's faulty.
Yeah.
So it never sways in its opinion about it, and it keeps broadcasting the faultiness out.
Yeah, kind of. Basically, the part about the removing the queue processes, it allows it's always going to suspect the queue has failed until queue decides to respond. So if queue might be just super slow, it'll eventually go to respond, giving its own S prime and removing itself. So that results in a final S that doesn't contain Q, because Q has announced, I'm alive. Don't put me in your suspected list.
So basically this is saying like, so the weakly consistent failure detectors, it's like eventually some process will know when something has failed, and then it's just broadcasting it to everyone else. If it broadcasts it to everyone else, then eventually they're all gonna get it. So then they become strong.
Yeah, it's something like the node that knows that it's alive, but unsuspected, eventually it'll talk with everyone in the node because it broadcasts its own suspected set to everybody else. Eventually, that node will get removed from the suspected list because of that last part, because of the removing the queue that sent you the suspected list. Because the weakly complete property says that at least one node knows at least one node knows who's failed. Now I confuse myself.
So to get the strongly complete, we need all of the nodes that are not faulty to at some point permanently know about the faulty node.
Yeah.
And broadcasting gives us
Yeah.
the weak guarantees that there is some node that permanently knows.
Yeah. So since you're taking the union of the sets, eventually the queue allows a suspected node to remove itself from the list, the remove queue, and the union, I guess, allows all the correctly suspected nodes to allows all the nodes that know that a process has failed to put that into the list. Okay, so eventually S will contain, because of the weak complete property, will contain a list containing nodes that have failed. Right? The weak complete property says that at least one correct node knows that suspects that a faulty node has failed. So at least one node will always know that a failed process has failed. So because it's constantly broadcasting, the failed node will eventually go into everybody's S sets, suspected sets there. But this remove queue part, which is basically remove the sender from my suspected set, because if you contact me, you're alive, it will remove all the correct nodes. So eventually, you're going to end up with just a set S of faulty nodes.
So it seems like that also has something to do with accuracy.
Yeah.
So, but the laws that you were talking about, or the properties that you were talking about earlier, don't mention, weak accuracy being equivalent to strong accuracy. It seems like that algorithm that you just showed would allow you to boost weak accuracy to strong accuracy as well, because the good nodes are broadcasting all the time and being removed from the suspected sets. But that's not included in the laws, so it seems like there must be some reason why that's not good enough for strong accuracy.
Strong accuracy is that
Never suspected this.
Yeah, if you suspect at one point.
if a correct node is suspected, then it can never be strongly accurate. It can be eventually strongly accurate. So
Okay.
the strongly accurate part is that no process is suspected before it crashes. But if a failure detector has
So, okay, I think I get what you mean. So why isn't there the same issue for boosting from like not eventual weak completeness to strong completeness? Because like the broadcast mechanism takes time, maybe an unbounded amount of time. So how can you? I don't even understand how the non-eventual versions can ever be there implemented.
Yeah, the paper mentions
Or how
that-
the boosting algorithm would work with them to.
the paper mentions that these strong the non-eventual accuracy failure detectors might actually not ever it might be
Okay.
extremely hard to implement. It doesn't talk about whether you can boost to. It doesn't talk about if you can boost the weak to the strong. It only states that the strong can do the same work. The strong has the same information the weak provides.
Right.
Yeah. I don't know if you can boost. I never looked too much into that.
Okay.
I think you get it. I don't know the answer to this, but I think it's not clear what is the message that you will be broadcasting if you are trying to boost the accuracy, right? Like consistency makes it simple. Like the thing that you want to just broadcast is the set of faulty ones, and then you just keep aggregating it and you're good. But if you're trying to boost the accuracy, you're trying to boost the complement of that. So it's not.
But it seemed like that's removing the sender from the faulty set. To me, that's as good as what it's doing for completeness.
Oh, I see. So as long as you're getting sort of a message from somebody.
Yeah. Like either way, it's gonna take some time, but eventually you'll get it unless you have a partition or something.
But the timing of the guarantees are reversed, right? So for completeness, you're saying that eventually everyone will suspect the faulty process. So you have the eventually count built in. For this, you're saying no one will ever suspect an unfaulty process.
Oh.
And the eventually here means after some period of running it, then we have the strong guarantee. But as soon as that strong guarantee time period kicks in, then you're again saying no one will ever suspect a non-faulty process. So they're sort of the opposite
Right.
of each other in terms of the timing.
Okay.
And that means that broadcasting doesn't have. We could maybe have a suspected suspect bucket and then pass that information around. Maybe do something like that seems weird.
Right, and also eventual means something different.
Right. Yeah.
Because eventual here means after some initial period of confusion, not like yeah, right, okay, I get it.
Yeah. I'm as confused as you are sometimes. This paper is really, really long. Okay. That was the
Sorry,
boosting.
just one thing. So maybe I'm a little confused, but to me it sounds like that the eventual strong accuracy is the same as strong completeness. Because at the end of it, you're suspecting all the failed nodes properly eventually somehow.
The accuracy doesn't give you any guarantee that you're suspecting all of the faulty nodes.
Okay.
It could be that you're not suspecting any nodes before they fail, but you're also missing all of the failed nodes. You have the trivial.
So accuracy is just that the nodes I know have failed, but that might not be the full list of failed nodes.
It's just a simplified version of precision and recall.
Okay.
Right? It's just like that's all they're doing here.
Okay.
For all that there exists, and those are the two sort of problems that they're playing with.
The trivial detector that never suspects anything gives you strong accuracy, but no completeness.
I drew a diagram of the boosting algorithm, which I tried. So you have three processes, P1 to P3. You have the suspected list. Let's say they all broadcast to one another. P2 broadcasts to P1, but P1's reply never comes because the network shuts down or something. P3 sends messages P1, but for some reason P1 just takes forever to process it. Maybe GC, I don't know, that happens. So then eventually you have that the failure detector for processes 2 and 3 both suspect that P1 has failed, even though it's still alive. If you ran the boosting algorithm once and P1 eventually applies, let's say it just doesn't go to P2. I just tried to be different there. Let's just say that message doesn't go. P3 does, so P1 does send to P3. So P1's not suspecting anybody, so you get the union of that. But you have to remove P1 from the suspected list because it contacted you, so you're gonna get the empty set. P2 will eventually get that message because of something called the reliable broadcast mechanism, which I'll talk about later. Eventually, P3 will send that same message to P2. That's an assumption in the paper. So later. So with the boosting algorithm, it means that the very weakest failure detector, the one in the bottom right of that table, the eventually weak accuracy and the complete failure detector is the weakest failure detector. It can be made to do the same thing as the eventually strong failure detector here. So when the paper says weakest failure detector for solid consensus, they mean diamond W here. But for the algorithms we're going to use, we talk about diamond L, the eventually strong failure detector, because if you don't, then your algorithm has to contain the boosting somewhere. So it's easier to save space in papers by just talking about this equivalent version that has less lines to write. So it means we only care about diamond L. The eventually weak accuracy, eventually strong completeness failure detector. There shouldn't be a eventually there. I made a mistake. It should be strong complete, eventually weak accuracy. So using this, we can then solve consensus. But before we can do that, we gotta talk about reliable broadcast. So all reliable broadcast it's a method of broadcasting messages so that eventually all processes will receive all messages sent, and they'll only ever see/process them once. So basically, the procedure to send is broadcast message, send it to every process. But when you receive a message, you check if you've seen it before. If you haven't, send it to all processes, and send one to myself also. Basically, it's gossiping. It's a way the paper authors can say that all nodes eventually get the message, and that all nodes in the consensus algorithm eventually get the message, and that they only receive it once. And this is the slide for code on consensus. I couldn't think of a good diagram for this, so it's just this. It's really hard drawing enough nodes to do this, so bear with me. I don't fully get this either. We have some assumptions though. We have that once a node fails, it never restarts. So it crashes forever. We have reliable broadcasts, so all nodes eventually get all messages, and they'll only get it once, or they'll only see it once. And that the failed nodes are less than half of all nodes. So it means that a majority of the nodes are correct. They never crash. If a majority of the nodes, or even 50% of the nodes, fail, you can't have a reliable broadcast, because a reliable broadcast depends on the majority of the nodes still existing, still have gotten the messages to be able to broadcast them out to everybody else. And also, you can't have consensus if half your nodes have failed, because of what a majority means.
Do they talk about what kind of network topology this is on?
Nope.
Do they?
Reliable.
Yeah. They only assume that you're in an asynchronous system. You have these assumptions. Network topology, all that depends on well, your network topology. Like, it's an implementation detail. This paper doesn't try to do any implementing. It only tries to describe a class of failure detectors that if you can create one, if you can implement one, you can solve consensus with it.
I'm just trying to envision an environment in which this reliable broadcast algorithm is interesting, because if all of your nodes are connected to each other, then you only need to send out the message once, and all of the other nodes will get it, right? On the other hand, if you're in an environment where you can have partitions, and nodes might not be able to get that message, then your reliable broadcast could fail if you partition the network in half. All of this half of it gets the message, deals with it, they're all done. Partition heals, no one on this side gets it.
So the partition is kind of assumed when you think about what it means to be in a pure asynchronous system. You don't know the upper bound of a message delay. You don't know the upper bound of processing time. So if you have a very, very long processing time or a very, very long message delay, you can't tell whether that's a partition or it's just taking a really long time.
So this is an environment where there are no partitions.
There might be no partitions.
I think we're guaranteed to have no partitions, but we can have arbitrarily long message. Is that right?
It basically comes down to the same thing because you can't detect it.
If I try to send you, so here's the difference. One is I try to send you a message and it might take me arbitrarily long to get to you. The other is I try to send you a message and it fails completely to reach you, it stops the transmission. And in that second one, you don't have reliable broadcast because if we have a partition across the middle of the network, half the network can resolve that message and be done with it, and it's gone. The other half never received it because the partition was complete, message is trying to get across failed.
But the thing is, you don't know it's failed because you don't have a failure detector. Is one thing. You don't know you have a partition.
But you also don't have reliable broadcast.
Yeah, but like that's why reliable broadcast depends on having a majority of the nodes being up. And that's why you have to broadcast to every node. So eventually the majority of correct nodes will have the message. But you can't just send one and assume that it'll eventually get everywhere. You have to broadcast it. So if you broadcast it out, you know that you're guaranteed in the sense, you assume that half the nodes get it, right? And the other half has failed. If they haven't failed, that message eventually gets rebroadcast to them by the other nodes. Because what do you do when you receive the message? You send it again to everybody else, if you haven't seen it before.
Right, but if you're saying that the messages can actually fail in transit between me and you, and I send you a message and it never gets to you at all, then what if all of these messages fail on the way to you if you're getting it? Then we don't have reliable broadcast, right?
Then I think you're a failed node if you have
Yeah.
half of the nodes.
I think based on like quorum, you would, instead of saying half, like for 3/5, those two missing nodes are the ones detected as failed by the majority.
Okay, but then later on, David starts getting messages and sending messages, and he hasn't failed, he just didn't get those messages. So I'm just saying if our network has the policy, has the property where a message actually can't get from you to you at all, it never gets to you, then I think we can't have reliable broadcast.
So I can't really answer that question. It's not covered in the two papers on unreliable failure detectors. It's covered in a previous paper by the author, one of the authors, Toueg. They have a paper on implementing reliable broadcasts in an unreliable environment. It's a separate topic that they just point to that I never actually read.
Maybe we'll
So-
do that one next
Yeah.
time.
That's a cop-out, but it's all right.
I think I think like for this paper they assume that the only crashes that occur are crash failures.
Yes.
So
Sorry,
the
that's
scenario
true,
that the reliable broadcast is trying to solve is if your sender say like sends it to three other processes and then crashes, then the others have to propagate it elsewhere. But it assumes that none of the links can fail. So if you send a message, it will eventually be delivered to the other process.
So the sender only gets barcodes if it's listed in the fails. Okay,
Yeah.
that's a good news. Right, it wants to send it to all of them, sends it to one and then it fails.
Yeah.
That one can broadcast, right? But it might fail for all of them. So, okay, thank you.
So I think part of the problems I've been talking about, like some of the imagery has the sending of a message failing, which I shouldn't have included because both papers assume we have reliable broadcasts. However it's implemented, we just assume we have it.
And hence a reliable network.
Yeah. Reliable in the sense that it was implemented so that it fulfills the properties of reliable broadcast. So probably some bad diagrams on my part there. Now, the consensus algorithm that I only partially get, it's been a fun presentation, hasn't it? Basically, a process starts, it picks a preference. So all this algorithm is trying to do is agree on a single value. You have a register that fits one thing. You want to agree on that value. You can do by induction, making a whole set of registers to do things, but at the basis, we just want to agree on one value. So so the process picks some value. It has some preference. Picks one. Starts with timestamp 0, and then starts rounds of the consensus algorithm, starting from 1 to possibly infinity. The first part is the process will send the round number, which acts as a timestamp, send the preference, send the round number they are choosing a preference for, sending their preference of value, and sending the timestamp they see. What time they think it is, to the coordinator. The coordinator in this case is one of the processes, is the coordinator, the leader. How they are elected is not covered in this paper. Election algorithms are a different thing, but for illustrative purposes, the paper just does number of nodes. They do some arithmetic with like the round number and like modding the number and getting the number out. So you send it to the coordinator. The second part is the coordinator. The coordinator waits for a majority of messages, so it knows that say there are n processes. It'll wait for n divided by 2 plus 1, or n divided by 2. Which one is bigger? It'll pick the preference with the biggest timestamp, which means that the preference it receives is just the one that the node thinks it's gone the latest. And then it sends that preference and the round number to all the processes. The processes are in part 3. They just wait to receive a round and preference prime message from the coordinator, or they suspect the coordinator has crashed. That's where the fit detector comes in. If they received something from the coordinator, then they change their preference to the one they received. They change their timestamp to a round, and then they send an acknowledge of that round to the coordinator. If they never receive anything, or they suspect the coordinator has crashed, they send a NAC to the coordinator.
Why would you send an act if you think the coordinator's crashed?
This is so that it never gets stuck in the face. I'll get to that in a second. acts and acts for that round. Once you receive a majority of them for that round, you go to this point. If you receive no acts and you just receive acts, you rebroadcast. So this is the part I'm a little bit confused about myself. But basically, let me check my notes. Oops. Okay, so if the coordinator receives no NACs, they rebroadcast the preference they have to all the other processes. If it does receive a NAC, it basically ignores all this and goes back up, right? So what's basically happening is that by the completeness property, there's going to be one node that's not being suspected that's not suspected at all. Eventually, when I think the idea is eventually when it becomes the coordinator, it'll either get all acts or some acts and some acts. Eventually, it comes down to the case where the coordinator is one that is not suspected. It's going to receive all the acts and no acts. So it's going to broadcast the preference it has because it's been acknowledged for that round to all the other processes. And when those processes receive that message, they all will have the same preference. They'll all have the same value. That's the part where they agree. So, is anyone else a little bit confused about this?
Yeah.
Yeah? Let's work through this together. What's the part that's confusing?
There's a lot of steps. So you can
Yeah.
I guess I'm a little confused on just the meaning of the preference and yeah, I guess what its meaning and purpose is.
The preference is just the value it has. The value the process is trying to agree on with everybody else. That's the preference.
We can think of that as
Okay.
Yeah, it's
So
kinda like last
the state to agree on.
Sorry?
like a last writer with
Yeah. So once a node fails, once it fails, it never restarts. So it's out of the game. So and because we assume that a majority of the nodes will never fail, will stay up, you eventually get to a point where you only have the live nodes.
Sorry, I didn't mean to interrupt. I was
Oh.
queuing a question for later.
Okay. So you have a majority of live nodes. So because you have a majority of live nodes, they'll eventually act and act here. And supposedly in the paper, eventually they'll all act here, which means they all got the same value for that round. Which is the part I don't really get.
So I think the knacking only happens when you suspect the coordinator has failed.
Yeah.
That's when you send the knack.
In the paper they say that this part in phase 3 is basically here to prevent the process, from freezing,
Right.
from waiting on one coordinator and never stopping. It has to do something.
And I think maybe what we're not seeing in this algorithm is that if I'm the coordinator and I get one or more knacks, then I have to hand off that coordination to another process.
Right, because if that coordinator received a knack, it couldn't have been from them. It
It would have been from some process
that failed or was suspected of failing. So the coordinator knows that it has to restart the whole, well, it has to try again, I think.
So if I'm the coordinator and I get a knack, then that means someone thought I was failing.
Yes.
And they couldn't get through to me. So
Yes.
I need to hand that off, the coordinator off to someone else.
So it goes back, yeah, it goes back up there and the new coordinator is struggling somehow.
That coordinator around
Yeah.
until we find one that isn't getting knacks.
Yes.
And as you mentioned in the beginning, we have the weak accuracy property here. So there is some process that no one will ever suspect of failing.
Yes.
And that process is going to end up being the coordinator.
Yes, so yes, you're right. Because of the weak accuracy property, there's one node that everybody suspects is alive, and knows is alive, and knows is alive, at least one. When that one becomes the coordinator,
They will only get acts from then on, and then
Yes.
they can start broadcasting out the preferences
Yes.
to everyone after some initial period of confusion
Yes.
before they become coordinator.
so yeah, because once a node fails, it doesn't come back up. Eventually, you're only gonna have live nodes, and eventually, from the live nodes, you end up on a coordinator that everybody knows is live. So after so many rounds, that coordinator will get axed, and you all have the same preference. And then once that happens, you're gonna go into an instant act loop, basically, because, yeah.
But every new round, we're all going to vote again, essentially, for our preference.
Yeah.
And then if I'm that healthy coordinator, I'll take all of our votes, consolidate them, and send out the results of that.
Yeah. Does that make sense?
The only question I have is like, so at what point, so where do we start the new coordinator selection process? Like, is it started by the nodes when they send out the knack, or is it started by the coordinator when it receives the knack? Or both times?
Like the other parts of this paper, the coordinator election depends on your election algorithm. So that depends. It's left to something else. They just talked about this part of the consensus algorithm. Like you notice that they also don't talk about where the nodes actually do any agreement. Like the nodes will have the right preference, so if you query all of them, a majority of the nodes will have the same value, which satisfies consensus, the distributed consensus. But they don't explicitly agree anywhere here.
The part where it says like, starts at line 9, wait to receive round preference prime from coordinator or to suspect coordinator. And then there's an if else. So how, if you're waiting to receive something, then is there an implicit time that you have to wait before you say I didn't receive anything to do the knack?
The implicit one is just until it suspects the coordinator, basically.
Sorry?
Depends on your failure detector.
It depends on the implementation of your failure detector. Yeah.
I get it. I didn't know.
Yeah, the else is the
So-
suspect part, and the receive is the if, the first if part. How your failure detector ends up suspecting depends on the implementation, which is part of why the papers don't discuss implementing. They give one idea where a failure detector could have a timeout, an ever increasing timeout. It has one set timeout. It suspects a node doesn't reply. It suspects that node. Eventually, if that node is not faulty, it'll send a message to that process through live broadcasts. So that process will remove that node from the suspected list and increase the timeout. And on and on and on you have timeout high enough that it covers how slow that process is, or that timeout just gonna keep increasing. There's no bound on it. That's one way of suspecting nodes.
Does that have weak accuracy?
I believe so. I forget which, that's the one partial implementation they leave in the paper. I forget which of the failure detector classes it was. But I believe it was weak. Yeah. Because it does end up suspecting something that might not have failed. So it couldn't satisfy strong accuracy. But it might satisfy eventually strong accuracy.
I don't see how you get even eventual weak accuracy out of that. Or you can, yeah, okay. You can get
Some eventually, like after some time of chaos T, where T could be in near infinity or
so
infinity
you don't
itself.
get weak accuracy, but you do get eventual weak accuracy.
Yeah, it's why the paper doesn't really care about the others. It just shows the relations and the equivalences. So if you can solve consensus with the weakest one, or the weakest the weakest failure detector, then we can implement these. We can implement the weakest. We might not be able to implement the stronger ones, but we know that the stronger ones can be covered somehow. Yeah. Or at least the stronger ones do the same work as the weaker ones, or with completeness, the weaker ones are equivalent to the strong ones. Yeah. And that's the actual consensus algorithm. I'm sorry I confused people. I was confused too. This was a learning experience. It's like being a TA again, where you get something wrong and the students talk to you. Hopefully, that gave you some interest in failure detectors and their place in distributed system history, and hopefully you'll read the papers or the related ones. Because that work, while nobody implements naive failure detectors like they're described in the two papers. One major reason is that if you think about how the messages are broadcast, that's a lot of messages. That's a lot of bandwidth usage. So no one really implements the naive version of weakest failure detectors described in the paper. Facebook used a offshoot of these failure detectors called the accrual failure detector in the Cassandra database, which is probabilistic. Instead of having a list of suspected processes that have failed, it just like a percentage that this process has failed, and it does some weird stuff to figure out like we should give up on this process or not. That's a whole nother possible papers you love talk. These were my references for this talk. Yeah, thanks. Now this is the end of talk. It's 8:15, so if you have questions, you can come up to me if you want. Is there still pizza and beer?
Yes.
Is there still pizza and beer if you want any? Otherwise, have a good night. If you want to talk at Cookies Love, you can contact me or Luke or James somehow. And yeah.